We're going to take a look today at something that we call a Taylor polynomial. Here's just a little background on Brooke Taylor. So let's start with something that we've seen before. We have a function, natural log of x plus 1. We want to approximate this with a straight line. We've called that the linearization in the past, or the tangent line approximation. So we want to find this approximation at x equals 0. So we need to find the y value that corresponds to 0. So plug in x equals 0, natural log of 1 is 0. We take the derivative to find the slope, and we evaluate that at 0, and we get a slope of 1. So the equation of the line, y minus y sub 1 equals m times x minus x sub 1. That simplifies down to y equals x. So our linearization equals x. So you can see here in red you have the function natural log of x plus 1. And we have the linearization, that tangent line approximation, y equals x. And if you look at that graph, these two curves touch when x equals 0, and near x equals 0, the tangent line is a pretty good approximation for the function natural log of x plus 1. But as you start to get further from that 0, that x equals 0, they really start to separate from one another. And it really doesn't take too long for that to happen. By looking at the graph, it appears visually that around 0.1 or 0.2, that separation starts to be noticeable. So this is a good approximation for values of x really close to 0, but as we move away from 0, the approximation is not nearly as good. So we want to see how we can extend this idea. Rather than finding a tangent line, maybe we could find a tangent polynomial that does a better job approximating the function, because a polynomial is going to have curves in it, and we can see if we can force those curves to follow along with the function we started with. So we're going to try to find a fourth degree polynomial to approximate natural log of x plus 1 at x equals 0. So we're trying to find a polynomial that behaves a lot like natural log of x plus 1. We'll use the notation p sub 4, so that means polynomial of degree 4. And it's going to have 5 terms. There's the constant term a sub 0, a sub 1 times x, a sub 2 times x squared, a sub 3 times x cubed, and a sub 4 times x to the fourth. These are all of the terms that could make up a fourth degree polynomial. And the way we force this polynomial to act like the function is to make all of their derivatives equal. So make both the polynomial and the function equal when x equals 0, make their first derivatives equal, which is what we do when we find a tangent line approximation, but we can also make their second derivatives equal their third derivatives and their fourth derivatives. And if all of the derivatives of both functions are the same, they're going to have similar behaviors. Okay, so here's what we're starting with. We have the function natural log of x plus 1. We're trying to find the fourth degree polynomial that behaves like natural log of x plus 1. So first, we'll find f of 0, because we're trying to find this approximation starting at x equals 0. So find f of 0, that equals 0, which means the polynomial should also be 0 when x equals 0. Well, if you replace all of those x's with 0, everything goes away except for a sub 0, which means if these two are equal, a sub 0 must equal 0. All right, so you can see I've gone in and I've replaced a sub 0 with 0, so we have that piece of the polynomial. And we're going to have to go through and figure out a sub 1, a sub 2, a sub 3, and a sub 4. All right, well, let's take the first derivative of the original function, evaluate that when x equals 0. Let's take the first derivative of the polynomial, so using power rule on all of these, the constant term goes away, bring the exponent down, reduce it by 1, so you can see we've done that. And now we evaluate the derivative when x equals 0, everything goes away except for a sub 1. Well, if f prime of 0 is 1, and p prime of 0 equals a sub 1, if those are going to be equal, then a sub 1 equals 1. So now we have a sub 0 and a sub 1 figured out. We're going to continue in this way to find a sub 2, a sub 3, and a sub 4. So right now we would have the first degree polynomial, which is our tangent line approximation. And we've already seen this. We have our original function, we have the tangent line. Now let's go ahead and see what degree 2 will bring us. So we take the second derivative of the original function. Evaluate that when x equals 0. We get -1. Take the second derivative of the polynomial. Evaluate that when x equals 0. And we get 2a sub 2. Setting these equal gives us a sub 2 equals -1/2. So we're getting closer to figuring out this polynomial. We have the polynomial of degree 2 figured out. So if we put that graph on, we can see that that remains close to natural log of x plus 1 a little bit longer than the degree 1 polynomial does. So it's a better approximation. All right, well, let's make our approximation even better by finding the third derivative. Evaluate the third derivative when x equals 0, and we get 2. Take the third derivative of our polynomial. Evaluate that when x equals 0. We get 6 times a sub 3. Setting those equal, we get a sub 3 equals 2/6. Now, I'm not going to simplify this, and we'll see later on why, but for right now, I just want to keep everything unsimplified. So here's my degree 3 polynomial. Let's see what that looks like. There was our degree 1. There's our degree 2. You can see it getting better. And you can see that gets even a little bit better. And now we'll find degree 4 by taking the fourth derivative. Evaluate it at 0, we get -6. Take the fourth derivative of our polynomial. Setting them equal, we get a sub 4 equals -6/24. So there we go. We found the fourth degree polynomial to approximate natural log of x plus 1. Let's go ahead and see what that looks like. So to take us through everything we found, we started with the first degree polynomial, and then we found second, fourth. And you can see it remains close to natural log of x plus 1, just a little bit longer. So to see where we started compared to where we finished up, you can see that, I can start to see that separation between the two curves for the tangent line right around point 2. And for our fourth degree polynomial, I don't start to see a separation till somewhere around point 6. So you can see that the two curves remain closer longer, meaning if we wanted to approximate natural log of x plus 1 using this fourth degree polynomial, that approximation would be much more accurate further from 0. So if we take a closer look at our fourth degree polynomial, we can start to notice a pattern that's occurring here. We have f, f prime, f double prime, f triple prime, and the fourth derivative. And the denominators, starting with the very first term, would be 1, 1, and then 2, 6, 24, which you might notice are factorials. So we can write it in this form right here. And notice some patterns here. We see some common numbers showing up. We have f over 0 factorial, and there's no x there, which would be x to the power of 0. We have the first derivative over 1 factorial times x to the power of 1. The second derivative over 2 factorial times x to the power of 2, and so on. This pattern occurs for all functions, so we can formalize this, and we call this a Maclaurin polynomial. A Maclaurin polynomial is always generated with x equals 0, and it always has this form. And now, thinking back to the previous problem, we've found the polynomial that approximates the function around x equals 0. Let's say we wanted to find a polynomial that approximates the function around x equals 1 or some other number. We can do that. It follows the same sort of pattern. We call that a Taylor polynomial generated at x equals c. And the difference here is you evaluate your derivatives at c, and rather than just multiplying by x, x squared, x cubed, you have to account for the fact that this is shifted over c units, and you have x minus c squared, and so on. But notice that they're essentially the same formula. The Maclaurin polynomial is really just a simplified version of the Taylor polynomial. If you replaced c with 0, it would give you the exact same formula you have up above. We want to find the 10th degree Maclaurin polynomial for the function y equals cosine of x. So if we recall, the formula for a Maclaurin polynomial takes this form, and we go out as far as we need to get the number of terms or the degree that we're looking for. In this case, we're looking for a 10th degree polynomial. So we need to find all these derivatives. The original function is cosine of x. Cosine of x evaluated at 0 because we're looking for a Maclaurin polynomial that tells us that we're evaluating this when x equals 0. So cosine of 0 is 1. Take the derivative of cosine, we get negative sine. Evaluate that at 0 and we get 0. Take the second derivative, third, fourth, and so on. And now you should recognize a pattern here with derivatives of sine and cosine. So if you really wanted to, you could go and write out all 10 derivatives, but you shouldn't have to. You should be able to identify the pattern that happens here. So now we go ahead and plug this into our formula. So f of 0 is 1, f prime of 0 is 0, f double prime is negative 1, and so on. And so all of those odd degree terms end up canceling out because they're multiplied by 0. And here's our 10th degree Maclaurin polynomial for cosine of x. So I want you to think about what this does for us. This polynomial should look a lot like cosine of x close to x equals 0. So let's go ahead and see what that looks like. Right, so if we go through and graph first our original function cosine of x, and this polynomial should resemble cosine of x. So let's look through one term at a time. Start with y equals 1. That's the tangent line, which is close, very, very close to 0. Now if we use the first two terms, so a degree 2 polynomial, you can see that this is much better than that tangent line. Let's go to degree 4, which is even better than 2, degree 6, degree 8, and degree 10. And you can see every time we add another term, the polynomial matches up with cosine incredibly well a little bit further. And it turns out with cosine of x, if you find a Maclaurin polynomial, the more terms you add, the better that approximation is going out towards positive and negative infinity. And just a side note here, if you're working on the calculator and trying to access a factorial to graph something like this, that button is located near the bottom right on your calculator. Right, so I'd mentioned how we add more terms and the approximation gets better and better, closer to the real function. It turns out, like I said, that goes towards positive and negative infinity. We can add more terms and it gets closer and closer, and we'll look later at how we can determine exactly how close that is. To get an idea of how good this approximation was, the actual value of cosine of 0.1, 0.995004, and our polynomial 0.995004. We go out even further, so go out to 1, so 1 unit from where we had our approximation centered. The actual function value 0.540302, the polynomial 0.540302, and we're not off until out at the 1, 2, 3, 4, 5, 6, 7, 8, 9th decimal place, which is incredibly accurate. And if we go even further out, go out to 4, you can see it's still a pretty good approximation. Cosine, negative 0.653, the polynomial, negative 0.685, just off by 0.02 or 03. All right, we want to find the 5th degree Taylor polynomial for cosine of x at x equals pi over 2. So this is the same sort of idea, but rather than centering this at x equals 0, we're centering it at x equals pi over 2. So we use that Taylor polynomial formula. And keep in mind this Taylor polynomial formula is basically the same as the Maclaurin polynomial, but since we're centered at a, we evaluate our derivatives at a. And if you just think of what you know about shifting polynomials left and right, you subtract that shift from x, so we take x minus a instead of just x. All right, so we take our original function, evaluate it at pi over 2, and we're going to go out to the 5th derivative. Okay, and now we can go and construct the polynomial using the formula. We can cancel out all those terms that are multiplied by 0, and here's our 5th degree Taylor polynomial centered at x equals pi over 2.